Welcome back, AP Statistics. This is Chapter 21, Comparing Two Proportions. Let's get to it. So we're going to be talking about comparing proportions, specifically with confidence intervals and hypothesis tests, which we've been talking about since Chapter 18. So suppose we wanted to estimate the difference between two population proportions, that's implied, or determine whether or not there's a significant difference between two population proportions. Well, of course, if we could study the whole population, then we wouldn't have to estimate anything, but if we wanted to estimate the difference between two population proportions using samples, or see if there's a significant difference between two proportions, we are going to employ a couple of processes we're going to talk about through this section. So to estimate the difference between proportions, we could perform a two-sample z-interval for the difference of population proportions. This is sometimes called a two-prop z-interval, a two-proportion z-interval. So not only is there a confidence interval for one proportion, we can find confidence intervals for two proportions, specifically a difference of proportions. Also, to determine if there's a significant difference, we could perform a two-sample z-test for the difference of population proportions. This is also called a two-proportion z-test, all right? So we can figure out about what the difference is, get a confidence interval for that, and determine if the difference is significant using the confidence interval and the hypothesis test, respectively. So, we need to talk about assumptions and conditions to compare proportions. Okay. First off, we need to assume independence of groups. This is a new condition, and we're going to start off with this one. We need to assume the two groups, the two samples we are taking are independent of each other, and there are some common violations of this that are a little sneaky. So here are some common violations of independent groups. We cannot collect data from matched pairs, okay? So, by the way, what are matched pairs? If we were to consider groups of two individuals at a time, sending one, let's say, to the control group and another to the treatment group, for example, sets of twins, or wives and their respective husbands, we cannot consider matched pairs. We can't just put one of the twins into the control and one into the treatment. We can't have one twin in one sample and the other twin in another. Same with wives and husbands and any other situation involving matched pairs. And that is because it is very likely that the opinions, interests, tendencies, whatever, of those in one group have influenced the other, all right? And twins have influence over another, wives and husbands have influence over another. That would violate the independence of groups. We can't compare proportions with one group of people from whom data are collected once before treatment and again after a treatment, okay? So if we have one group of people and we do a pre-test, post-test kind of thing, we take some information on the group before we apply treatment and then apply the treatment and see if the results change afterwards. We cannot do what we are studying in Chapter 21 if that is the case. Here's why. We cannot compare pre- and post-test scores for the same group since subjects' performance after treatment could be related to their performance before treatment. All right, so we can't conclude that the treatment is what caused the difference because their performance pre-treatment could influence their performance after the treatment. So these are the two situations in which we cannot conclude that we've satisfied the assumption of independent groups. Namely, are there matched pairs? If there are matched pairs, we cannot perform any inference with the difference of proportions. And if we are sampling the same group of individuals twice over, we cannot conclude independent groups. So there are some assumptions and conditions that we need to consider that We've seen many times before, as Chet Baker once performed, it's always you. Always you guys. Independence within groups now. So not only independence between the two groups, but independence within each group must be assumed. So within each of the two groups you're considering, data should be based on results from independent individuals. We could assume this by checking the, you guessed it, randomization condition, always you. Data should be drawn from a random sample or treatments should be randomized. And the 10% condition, the sample should not exceed 10% of the population. We also need to acknowledge the success-fail condition. Both samples are big enough that at least 10 successes and 10 failures have been observed in each. Okay? So both samples are big enough that at least 10 successes and 10 failures have been observed. Okay? All right, so among randomly sampled teens aged 15 through 17, 57% of the 248 boys had posted online profiles compared to 70% of the 256 girls. Question: can we use these results to make inferences about all 15 to 17-year-olds, specifically regarding their online presence? Well, let's see if we can do that. Randomization condition. The sample of boys and the sample of girls were both chosen at random. Randomization condition, check, move on. 10% condition. 248 boys and 256 girls are each less than 10% of all teenage boys and girls. That is an understatement, of course. Independent groups. We got to check for independent groups here. Because the samples were selected at random, it's reasonable to believe the boys' online behavior are independent from the girls' online behavior. This is admittedly just what it is, an assumption, all right? There's no reason to think that they were matched pairs. This is groups of brother and sister. There is no evidence that there was a pre- and post-test of any kind. These are clearly two different samples. They are not related, and so we can assume independent groups. And success-fail. Among the boys, 57% of 248 is 141. That is greater than 10. And 248 times 0.43 is 107, did not, also greater than 10. For the girls, 256 times 70% is 179 successes. 256 times 30% is 77 failures, both greater than 10. We can move on. All right, so now we're going to talk about the 2 proportion Z interval. This is straight out of your textbook. There are some familiar characters here, though this looks a bit messy. I promise that this is familiar enough to make sense of it. So we've met our conditions. We're ready to find a confidence interval for the difference of 2 proportions. The confidence interval is we take the difference of our sample proportions as a central point, and then we form the extremities of the confidence interval by adding for the right endpoint and subtracting for the left endpoint the Z star value, and you know the Z star values for a couple of confidence levels. And then you have the standard error. All right, so that is familiar to you, but it's a special standard error. It's a standard error for the sampling distribution of the difference of sample proportions, all right, which you will note, if you've been paying very close attention, is different than the standard error for the sampling distribution of one sample proportion. Of course, it doesn't hurt to talk about these Z star values that we commonly see. We have 90% confidence, 95% confidence, and 99% confidence. Z star values are given. Any other confidence level, if you're given something different than 90, 95, or 99%, you want to find a Z star value, you would use inverse norm, mu equals 0, and standard deviation equals 1. If you have a newer calculator, you can select center and put your level of confidence verbatim in your area. If you have an older calculator, you got to be a little bit more creative, and I definitely recommend drawing a picture to help. All right, but I want to take a special note here of the 95% confidence interval. Z star is 1.96. 95% confidence is kind of sort of the gold standard for confidence levels for intervals that we use in statistics. And the reason for that, literally, and this is not the only time this kind of thing has happened in statistics, is because Sir Ronald Fisher who famously put out a work called Design of Experiments. The Design of Experiments lived between 1890 and 1962. He loved the 95% confidence interval. Now, why he loved it so much, I'm not sure. It's a good happy medium between 90 and 99%. The Z-star value is dangerously close to 2. There are a lot of things to love about 95%, and Ronald Fisher recognized that and kind of sort of made that the gold standard for confidence intervals. So here we go. What we're going to do is we're going to take some information from the top here, and we're going to apply it to the problem we've been working on. We have 57% of the 248 boys posted online profiles, 70% of the 256 girls. We calculated the standard error for the difference of sample proportions is going to be equal to 0.0425 and found the assumptions and conditions required for inference checked out okay. Now, how do we get this standard error? There is a formula on the other slide. You would just plug the values in and you would get this number. Fortunately for us, the calculator can do that just as well without all of the strenuous little inputs. We could just go to two proportion Z interval and take it from there. And I'll show you how to do that. But we're given a standard error here, and we can use that. What does a confidence interval say about the difference of online behavior? Well, we have this 95% confidence interval. We have this right here. We're going to do the proportion of girls minus the proportion of boys. It's nice to keep things positive. Z-star is 1.96. Ronald Fisher would be proud. And we have the proportion of girls minus the proportion of boys standard error. And that standard error we get from the problem up here. Very good. Just use that formula from that prior slide that I showed you, plug values in, and you got it. And we would get 13% plus or minus about 8 1/3%. All right, so that's going to be between 4.7 and 21.3%. And there's a reminder to myself. We can be 95% confident that among teens aged 15 through 17, the proportion of girls who post online profiles is between 4.7 and 21.3 percentage points higher than the proportion of boys who do. This provides evidence that teen girls are more likely to post profiles than are boys the same age. All right, and that is our conclusion from our confidence interval. All right. So let's find a two proportion Z interval using the more conventional method of the graphing calculator. A Gallup poll asked whether the attribute intelligent described men in general. The poll revealed that 28% of 506 men thought it did, but only 14% of 520 women agreed. We want to estimate the true size of the gender gap by creating a 95% confidence interval. So here's how we shall do it. We need to first check all the assumptions and conditions. So refer back to those assumptions and conditions in your notes or prior in the video, and make sure that this example fits all of the criteria. And one of the criteria is actually a bit suspect, and we'll talk about that. Number 2, we're going to let P1 be the proportion of men who find intelligent to describe men in general, and let P2 be the proportion of women who do the same. Find a 95% confidence interval for P1 minus P2 using the graphing calculator. We'll get to that in just a moment. And the last step will be to interpret the confidence interval in the context of the problem. So we'll start with number 1. We're going to check all the assumptions and conditions. So we can assume that men and women are independent groups. All right, that one, unless there is a clear reason to think that the groups are not independent, we should assume independence there. So unless we're dealing with matched pairs or before and after study, or there's any reason to think that the groups may have influence on each other, we will assume that they do not, and we can move on. However, there is no clear evidence that the men and the women were selected at random. Okay, there is nowhere in this example where we can determine that the men and women within their groups were selected at random. So that's a little suspect, and I would like to know more, but moving on. 506 men and 520 women are far less than 10% of the population of men and women, respectively. And we observed 142 successes, that is 28% times 506, and 364 fails. That would be the number of fails out of the 506 men. And 73 successes, that is 14% times 520, and consequently 447 fails for the women, all greater than 10. So we have met all of the assumptions and conditions, save that randomization condition, and so we'll have to take our results with a grain of salt. Now we're going to use the graphing calculator to find that confidence interval. So here we are at the calculator. We're going to go to stat, and we're going to go to tests, and we're going to go to 2 proportion z interval. That is pretty far down. 2 proportion z interval, that's letter B. So now we have x1 and n1. This is going to be our proportion for the men. We're going to start with 28% of 506, which will automatically output 141.68. Now we need to be conscientious of our rounding here. This is going to be 142 men, okay? You would round appropriately. If you put a decimal in for x1, your calculator will throw a fit at you because that means that you counted a part of an individual in your study, which is impossible. In the words of Dr. Seuss, person's a person no matter how small. All right, so we'd say 506 would be the sample size for the men. Now for the women, we have 14% times 520, and that would give us 72.8. Again, we would round up to 73, and we would say 520 for the women. Now the confidence level is 95%, very good. Ronald Fisher would be proud, and here we go. And there is our confidence interval. So we take those upper and lower limits, and we say the difference of the proportions P1 minus P2 is between 9.1 and 18.9% approximately. So how do we interpret that confidence interval in the context of the problem? Well, here is one way we could do it. We can be 95% confident that the difference in proportions of men and women who attribute intelligent to men in general is between 9.1 and 18.9% in favor of men. So men think they are intelligent in general, more so than women, to the tune of somewhere between 9.1 and 18.9%. Let's end the lesson with one more practice problem. A public broadcasting station plans to launch a special appeal for additional contributions from current members. Unsure of the most effective way to contact people, it runs an experiment. It randomly selects 2 groups of current members. It sends the same request for donations to everyone, but the request goes to one group by email and the other group by regular snail mail. The station was successful in getting contributions from 26% of its members at email, but only 15% of those who received the request by regular snail mail. A 90% confidence interval estimated the difference in donation rates to be 11% plus or minus 7%, most certainly in favor of the emails. So let's interpret the confidence interval in this context. Think of how you would do it, pause the video, try it on your own, and unpause the video when you think you have an answer. All right, I'll assume we're ready to continue. Here we go. We can be 90% confident that the proportion of contributors who received an email is between 4 and 18% greater than the proportion of contributors who received a letter in the mail. All right, so let's look at number 2 now. Based on this confidence interval, what conclusion would we reach if we tested the hypothesis that there is no difference in the response rates of the 2 methods of fundraising? Explain. All right, so how would you answer that? Think about how you would answer that. Pause the video and unpause when you have an answer. All right, here we go. Since the confidence interval doesn't contain 0, that is, no difference, we reject the null hypothesis. There is a significant difference between the rates of contribution for recipients of emails and letters in the mail in favor of the former. In other words, if our confidence interval yields between 4 and 18% in favor of the emails, then there is definitely a difference in how often we get contributions from those two groups. So we would reject the null hypothesis of no difference and side with the alternative that there is definitely a difference in favor of the emails.